Okay, so in the last lecture we saw the electron self energy diagram, and we have seen how such a diagram gives a contribution to the mass of the electron. In this lecture we will consider a diagram of this kind where there is a fermion in the loop. So, this is the at one loop level, this is the last diagram that we need to consider. You have a virtual photon of momentum, let us q, and there is a pair created here which is subsequently annihilated, and finally, you again have a virtual photon. If I denote this momentum here to be k, then this will simply be k plus q, and we need to consider the contribution of this diagram, a diagram of this type, to the photon propagator. This is what we will discuss in today's lecture. So, we can use the Feynman diagram. We know what. So if we forget about the these two photon propagators, then the contribution from this loop will be given by, first you have a vertex here, for which I will put minus I E 0. In this lecture I will denote E 0 to be the charge of electron instead of E. At the end of this lecture you will see why E 0 instead of E. So, you will have I E 0 gamma mu for this vertex. Then you have a fermion propagator which goes like I divided by k slash minus m, and you have for this vertex again you have a factor of minus I E 0 gamma nu, and for this fermion propagator it is I divided by k slash plus q slash minus m, and there is a closed fermion loop for which you have to put a factor of minus 1, and you need to trace over this, and because there is a loop here, you have to also integrate over the loop variable k. So, you have d 4 k divided by 2 pi to the power 4th and this. So, this is what you will get from a closed fermion loop like this. This is, I will denote this to be I pi 2 mu nu of q. If you integrate over k, the only thing that will be left is q. So, pi 2 will be a function of q, and as usual 2 for, because it is second order in E 0, it is this the contribution is of order E 0 square. That is why I denote it as pi 2, and this is what you will get. We will evaluate this diagram explicitly little later. First, we will discuss what the physics of such a contribution here. As usual, we will denote all the one particle irreducible diagrams to be like this. I will write here as 1 pi. This will be all diagrams which are actually irreducible, in the sense if you remove any of these internal lines, then the diagram is not separated into two parts. So, all such diagrams I will denote them like this, and so sum of all such diagrams I will denote by this symbol here, and I will define pi mu nu such that I pi mu nu of q, if this is q, is given by the contribution from such a diagram. So, this is what I will denote to be I pi mu nu of q, and then the full propagator will actually be given by the full photon propagator to all orders will be determined by taking sum from all such diagrams. So, you have at tree level you simply have this, at after that you have only one such term here, then and all such one particle irreducible diagrams included like this. So, this is what is going to give us the full photon propagator, and I will denote this by the symbol. This full propagator is given denoted by this symbol. This is what I will get. So, we would like to know what this quantity here is. Even before we try to compute this quantity, we can see what form this this object can take place. Okay. So, using symmetry arguments and word identity, we can conclude, we can determine, we can get the most general form that that this guy can take place. First of all, you know that this is a symmetric function, and also it can only contain, it can only be functions of q. So, the only thing that it can be a function of is eta mu nu, which is a symmetric second rank tensor, and in addition you can have q mu and q nu, q mu times q nu. So, the most general form for pi mu nu will be I pi mu nu, or pi, as for simplicity pi mu nu simply will be A times eta mu nu plus B times q mu q nu. But now, if we use word identity, which basically says that q mu pi mu nu equal to 0, then this immediately gives me. So, the first term A times q nu, and from the second term I get plus B q square q nu equal to 0. Therefore, A equal to minus B times q square. So, therefore, the word identity implies this to be minus 1 over q square. This is what you will get, where this quantity can actually be a scalar function of q. So, therefore, this A, I will denote this to be some pi of q square, where pi is a scalar function, and then the tensorial structure is given by this term here. So, this is the most general form that pi mu nu can take. Therefore, all we need to do is we need to compute pi here. So, once we know that the one particle irreducible diagrams will give a contribution which is of this form, we can now come back and then we can compute the full propagator, the exact propagator to all orders in perturbation theory can be computed by summing over all such diagrams, and this is given by. So, the tree level term will give me. So, I will write this equal to this at tree level I will have minus I eta mu nu q is the momentum, then this will simply be q square. This is from this term. Here you will have one photon propagator, which will simply be minus I eta mu rho over q square. Then you will have this, which I denote to be I pi of rho sigma, and you have finally the photon propagator here, which is again given by minus I eta sigma nu divided by q square. Then you have a diagram here, which will have two such term and so on. So, this is what you are going to get here. Now, suppose I will introduce this function, this tensor here delta of rho sigma to be delta rho sigma minus q rho q sigma divided by q square. Then you can see this quantity here, if I multiply this with this, then I times minus I gives me plus 1, and this here will simply be so pi of rho sigma is simply eta rho sigma minus q rho q sigma divided by q square. To that I will multiply by eta sigma nu. So, if I have eta sigma nu, then you have eta sigma nu. So, it is basically delta of rho nu minus q nu q sigma q nu q rho divided by q square. So, this is this delta of rho nu. So, this is what I will get if I multiply I eta sigma nu with I times pi rho sigma. I will use for pi of q square, I will use this notation here. Remember, you have this q square in this term. So, I can as well write it as q square times this times pi of q square. So, my definition of pi of q square will involve a q square here. So, in terms of that, this is just for convenience, so that I will not have a 1 over q square here. So, eta mu nu times eta rho sigma divided by q square minus I times I pi is given by this times pi of q square here. So, you will have a factor of pi of q square here, and then finally, you have pi of q square. So, this is just to say that if I leave the first term here, then the second and third term, the product of second and third term is nothing but delta rho nu times pi of q square. So, if this is my delta rho sigma, then what I get here is this term here is given by first term is going to remain as it is. So, it is I eta mu nu divided by q square, and the second term, to emphasize what I said, I denote pi of rho sigma. I know pi of rho sigma can only take this form. It can be given by q square eta rho sigma minus q rho q sigma. Word identity uniquely determines this form times some scalar function of pi of q square, which we need to determine by doing explicit computation. So, if this is what is pi of rho sigma, then this term is given by minus I eta mu rho divided by q square times the product of these two terms is simply delta sigma is contracted. So, delta rho nu times pi of q square. The next term will again be, it will involve 1 minus I eta mu rho divided by q square. Then you will have delta of rho sigma, delta of sigma nu pi of q square whole square, and it will continue. So, this is what we are going to get. All right. So, this the first term is given by this, the second one is this one, and then the third diagram will give a term like this, and then so on. Now, you notice if this is our delta rho sigma, then delta rho sigma delta sigma nu is merely given by delta rho sigma minus q rho q sigma over q square times delta sigma nu minus q sigma q nu divided by q square, and the first term when it multiplies here gives me a delta rho nu, the second term minus q rho q nu divided by q square, this term here minus q rho q nu divided by q square, and the last term here plus, you can see q rho q nu, again there will be 1 over q fourth here, but q sigma is again q square. So, this will be plus q rho q nu divided by q square, this will cancel, and as a result this is merely given by delta of rho nu. So, this quantity here is simply delta of rho nu, and that will keep continuing. So, what we can do is that we have a common factor I eta mu nu over q square, or so I can write the first term as minus I eta mu rho delta of rho nu over q square. Then I eta mu rho is there in all terms. So, I can write it as I eta mu rho divided by q square times this Kronecker delta rho nu, and then the second term will give me delta rho nu pi q square, the third term delta rho nu pi q square whole square, and so on. This is what I am going to get. The first term also I can write it as delta rho nu is delta rho nu plus q rho q nu divided by q square. If I substitute it here, then this is going to give me minus I eta rho nu over q square. There will be a delta rho nu in all terms. So, I will get delta rho nu, and then whatever left is a geometric series, it is 1 plus pi square and so on, which I will simply denote as 1 over 1 minus pi of q square. And finally, because I have a Kronecker delta here instead of this, I will get an additional term here, which is given by minus I eta mu rho divided by q square times q rho q nu divided by q square. This is what I am going to get at the end of the day. All right. So, what I have here is a simply minus I eta rho nu over q square delta rho nu divided by 1 minus pi of q square, and here minus I, this can contract and it will give me q mu q nu divided by q to the power 4th. This is what I am going to get. I can simplify this eta rho nu if I multiply it with sorry, it is eta mu rho, it is not eta rho nu, it is eta mu rho. So, I have a eta mu rho in this term. If I multiply eta mu rho by delta mu nu, what I will get is simply I take minus I q square times 1 minus pi of q square. So, minus I divided by q square 1 minus pi of q square times this is merely given by eta mu nu minus q mu q nu divided by q square. That is the first term, and the second term is simply given by plus minus I over q square q mu q nu divided by q square. So, this is what I will get for the full propagator. Now, this quantity has to be considered. For example, suppose we consider any physical process, then this will contribute to the S matrix. When we evaluate this in the matrix elements of the S matrix, we already know this there will be 3 terms here. First term eta mu nu times this, the second and third term are of this form. So, for example, finally, we know that whatever quantity we will get some chi mu nu kind of thing, it will have this form A eta mu nu plus B q mu q nu and so on. This quantity the S matrix will have a term like that, and then it need to satisfy the word identity. So, the word identity basically says that q mu times this equal to 0. Therefore, whenever you have, so therefore, you have a q mu here, you have a q mu here. So, if q square is non-zero, then this B will have to be equal to 0. Therefore, the word identity tells that although the full propagator for the photon has all these term here, if we want to, if we evaluate the S matrix elements, then this term here in the second term in this expression as well as this term, they will not give any contribution. The contribution coming from these two terms will they will simply vanish, they will cancel, and finally, it will become 0. So, for the purpose of computing the S matrix element, the full propagator is given by this term here. Therefore, the full propagator, we will simply write the full propagator to be. So, you can see that this the word identity plays a very important role here. Without doing explicit computation, we can tell the form of the exact propagator by using the word identity, and for the photon propagator, this is simply given by minus I eta mu nu divided by q square times 1 minus pi of q square. This is what is this propagator. Now, what we will do is that we will see what this propagator can do for us. First of all, this pi of q square, if you remember, this is this is given by these one particle irreducible diagrams. This is our pi of q square, and so this is pi mu nu q square, I pi mu nu q square, where pi mu nu is merely given by q square eta mu nu minus q mu q nu times pi of q square, and this diagram does not contain any internal photon line which is massless. Therefore, this pi of q square, because of this fact, this pi of q square is going to remain finite. If I just consider this term here, this diagram contribution from this diagram, it does not have any massless propagator here. So, therefore, q square does not vanish, therefore, this quantity is finite when q square equal to 0, because q square the full photon propagator has this form. Therefore, this this result basically tells that the full propagator actually has a simple pole at q square equal to 0. So, it has a pole at q square equal to 0. Remember, in contrast, when we evaluated the electron self energy diagram, we did not have a simple pole, we had a simple pole at p square equal to m square, but in addition we had double pole, triple pole and so on at p square equal to m square, and when we summed up all contributions, we at the end of the day we got a simple pole which is given by p slash minus m 0 minus sigma of p slash or something like that. When we summed all diagrams, we got we got a term like this. Therefore, this pole here is the simple pole actually got shifted because of the higher order contributions. Unlike the electron self energy case, here the pole is not shifted, we still have, because pi of q square is pi of q square does not have any pole, it is actually regular at q square equal to 0. Because of that, the exact propagator has a simple pole at q square equal to 0, and therefore, the pole is not shifted, and because of that the photon remains massless to all orders in perturbation theory. It is massless to all perturbative orders. So, therefore, the mass of the photon is not shifted because of these corrections. So, what do they do? What do this propagator do actually? To understand that, we can consider the S matrix elements for some physical process. Let us say, for example, you have electron scattering or something like that, and let us assume that the scattering is actually by a low energy photon. Then the full diagram here will be given by this, the full photon propagator is given by this. So, if, at the tree level, if you had nothing, what you would have is, you would have got for this propagator, you would have got a contribution minus I e square divided by q square eta mu. So, you would have got a factor of minus I e from here, minus I e from here. At the end of the day, you would have got, if E 0 is the charge of electron, then you would have got E 0 divided by q square for such a diagram. Instead, when you sum up all such diagram, you do not get this. If you include this quantity is simply replaced by this times eta mu nu. This is what you would have got, or this is what you get from this propagator at tree level. Now, if we include all the quantum corrections, then instead of this, we have just now showed that what we get instead of this is simply eta mu nu divided by q square times 1 minus pi of q square times E 0 square. Okay. And suppose this is a low energy photon, the virtual photon is low energy, then you can say that this is merely given by eta mu nu times some Z3 E0 square divided by q square, where Z3 is given by 1 minus pi of 0. So, suppose you are evaluating this near q square equal to 0, then you can simply replace here, instead of pi of q square you can replace it by pi of 0, and I will define Z3 to be 1 over 1 minus pi of 0. So, therefore, this quantity is nearly equal to this when q square is small. So, the role of these quantum corrections, as we have seen, instead of simply E0 square eta mu nu, which you get at tree level, when you include quantum corrections you get Z3 times E0 square eta mu nu divided by q square. So, the role of this term here actually basically modifies the charge of the electron, it renormalizes the charge of the electron, and E0 is replaced by E, which is given by square root of Z3 times E0. E0 is known as the bare charge of the electron, E is the physical charge of the electron, and the bare charge times square root of Z3 gives the physical charge of the electron. Any physical process sees only the physical charge of the electron, and all these quantum corrections are encoded in this term pi of q square here, or in the term Z3 here. So, this is what you will get for when q square is close to 0, but any finite q square you consider, this is what is the contribution that you get. So, effectively you have an effective charge of the electron which depend on q square. So, the charge, or if I just denote alpha equal to E square divided by 4 pi, then the effective alpha, effective fine structure constant, basically is given by E0 square divided by 4 pi times 1 minus pi of q square, and the effective fine structure constant is dependent on q square, and the full form of the fine structure constant is given by this expression, and this pi of q square contains the information about all the quantum corrections. At tree level to 0th order, if you consider merely a process like this, then you get alpha is simply E0 square divided by 4 pi. However, the quantum corrections modify this, and then this is what you get. And so, if we know what is pi of q square, then we know what is the effective coupling here, and this pi of q square that we can explicitly determine order by order by explicitly computing all the diagrams. So, let us now compute this pi of q square at least to the second order. At one loop, this pi of q square is simply given by pi 2 of q square, and we know how to do the loop integration. So, this is what we will discuss in the remaining part of our lecture. So, let us do a computation, and let us get the expression for pi of q square at one loop. So, what we would like to do is one loop, we would like to compute the one loop contribution to pi mu nu of q square, or simply pi of q square, equivalently pi of q square. This again, so we need to consider this diagram here. This is q, this is k, and this is k plus q. This is mu nu. We know what is the amplitude for such a process. This is basically given by So, this is I by 2 mu nu of q square, and this is simply minus E 0 square integration d 4 k divided by 2 pi to the power 4th trace of gamma mu 1 over k slash minus m gamma nu 1 over k slash plus q slash minus m. This is what we have, and we would like to evaluate this integration here. So, I will rewrite this term to be minus E 0 square d 4 k over 2 pi to the power 4th trace of gamma mu, then this will be k slash plus m here gamma nu k slash plus q slash plus m divided by k slash k square minus m square times k plus q square minus m square. So, this denominator again as usual we will use the Feynman parameterization to rewrite this denominator as an integral of x, and the numerator it is just a trace involving 4 gamma matrices. So, it is very straightforward, we can work it out in explicitly. So, let us do that. The denominator is given by one over k square minus m square times k plus q whole square minus m square, and this quantity I will write it as integration 0 to 1 dx times 1 divided by k square plus 2 x k dot q plus x q square minus m square whole square. This is what I will get when I use the Feynman parameterization. And now again you see there is a linear term in k and there is a quadratic term in k. I want to complete the square. So, I will introduce the variable L, which is basically k plus x q, and I will express it in terms of L square. When I do that, what I will get is it is simply 0 to 1 dx 1 over L square minus delta whole square, where delta is basically is given by m square minus x into 1 minus x q square. So, this is what delta is. So, this is what I will get in the denominator. Numerator again I can simplify this. So, the numerator is given by trace gamma mu k slash plus m gamma nu k slash plus q slash plus m, and this is nothing but I can rewrite this as trace of gamma mu k slash gamma nu k slash plus q slash plus m square trace of gamma mu gamma nu all other terms involve 3 gamma matrices whose trace vanish. So, this is what you will get, and this term here is merely given by 4 eta mu nu m square, and this term involves 4 gamma matrices. We know what is the trace of 4 gamma matrices. So, you have trace of gamma mu, gamma nu, gamma rho, gamma sigma is basically given by 4 eta mu nu, eta rho sigma minus eta mu rho, eta nu sigma plus eta mu sigma, eta nu rho. So, this is what we already know. Using this we can simplify that, and when we use that, finally what we will get is 4 times k mu k plus q nu plus k nu k plus q mu minus eta mu nu k dot k plus q minus m square. This is what is my numerator, but now I have introduced this variable L here, which is k plus x q, and I would like to express this numerator in terms of L. And I know in the denominator is a function of L square. So, I will rewrite it, I will write it in the variable L, using the variable L, and I will keep only terms which contain even powers of L. For example, if I have a L mu, I will keep it. If I have a term which is linear in L mu, then that will give a 0 contribution when I integrate it over all values of L. So, keeping that in mind, what I have is 4 k equal to L minus x q. So, this is L minus x q mu L plus 1 minus x q nu plus L minus x q nu L plus 1 minus x q mu, and finally, here minus eta mu nu times L minus x q dot L plus 1 minus x q minus m square. This is what I have. And so, what I will get here is, I will just get 4. This will give me L mu, L nu. This will again give me L mu, L nu, L nu, L mu. So, I have twice L mu, L nu. L mu times this will give a term which is linear in L mu. So, I will not write it. However, this term multiplied by this term gives me minus x times 1 minus x q mu q nu. I will get one such term from here. So, this is minus 2 x 1 minus x q mu q nu. Finally, I have, so this is the contribution from these two terms, and this term here will give me minus eta mu nu times, here it is L square, then minus x into 1 minus x q square. The other two terms are linear in L. So, I will not write them, and finally, minus m square. So, this is what I have for the numerator. Okay, so when I put everything together, what I will get now is I pi mu nu, I pi 2 mu nu of q is going to be, there is a minus e square and this is 4. So, minus 4 e square integration. Now, I have I am using the variable L. So, d 4 L divided by 2 pi to the power 4th and then x is integrated from 0 to 1 dx. This is what you have in the numerator except the factor of 4. So, I have 2 L mu L nu minus eta mu nu L square minus 2 x 1 minus x q mu q nu plus eta mu nu m square plus x into 1 minus x q square. This is in the numerator, and in the denominator I have L square plus delta whole square. We need to evaluate this integration here. We can, for where delta is given by m square minus x into 1 minus x q square. This is what we will evaluate. We can further simplify this term here. Remember, suppose you have some f of q square or f of L square, some function of L square L mu L nu. When you integrate it over L, when you integrate d4 L at the end, because it is symmetric in L, the only thing that you can get is some quantity times eta mu nu. If you contract this with eta mu nu, what you get here is L square f of L square dx d4 L is simply a times eta mu nu which is 4a. Okay. On the other hand, if you consider L square, so therefore, in this integration, your a is merely given by this divided by 4, this equal to a is this divided by 4. So, this integration here, in this integration you can merely replace L mu L nu by L square divided by 4. Okay. So, this is what you can do. If you have L mu L nu inside the integration, then this is merely given by eta mu nu L square divided by 4. This is what I can use here. So, when I do that, I will simply get eta mu nu divided by 4 times L square. So, this we need to evaluate. This is again going to be a divergent integral. First, we need to do a Wick rotation, Euclidean continuation, and write it in terms of the variable L e square, and then finally, we need to evaluate this integral here. It will again be a divergent integral. It is, in fact, it is going to be quadratically divergent. So, what we will do is, we will in the next lecture, we will first introduce a UV cutoff, and then we will evaluate this integration explicitly. We will see that this is quadratically divergent. In fact, if we use a UV cutoff, then pi mu nu does not preserve Ward identity, it violates Ward identity. So, in the next lecture, we will introduce another regularization, which is known as the dimensional regularization, and then we will evaluate this integration by using dimensional regularization, and then we will see that the dimensional regularization in fact preserves Ward identity. Finally, using the dimensional regularization, we will evaluate the one loop contribution to the photon propagator. This is all we are going to do in the next lecture.